Hi everyone. So in this video, I'm going to be walking us through some problems under U-substitution. So basically, I'm going to be walking us through some problems on how to use U-substitution or when to use U-substitution. So the general strategy is this. For example, if we have the integral of f of g of x multiplied by g prime of x dx. So how do we integrate this kind of thing? For example, let's take we have f of x being equals to x squared, and we have g of x being equals to sine x. So if I ask you what is f of g of x and what is g of f of x, so what's going to be your answer? Now, what is f of x? F of g of x. So basically, anywhere we see x, we're going to represent it with what? G of x in the function x. So basically, we're going to have this to be sine x all square. How about g of f of x? So basically, anywhere we see x in g, we're going to represent it with the function f of x. So that means we're going to have this to be sine x squared. Now that we've established what we mean by f of x of x, f of g of x, and g of f of x, so the question is that how do we integrate this kind of function here? So here we can observe this. We have f being a function of g of x and is now being multiplied by derivative of g of x. So basically, anytime we have a function multiplied by the derivative of something, so we need to check if we can extract. Okay, let's take for example, let's say we make u to be g of x, and if we differentiate u with respect to x, we're going to have this to be g prime of x dx. Now if we substitute everything here, so that means we're going to have f, so g of x being u, so we have u, then we have g prime of x dx being our du. So we can see that the integral of f of g of x multiplied by g prime of x multiplied by dx is simply the integral of f of u du. Now let's look at some practical examples on how we can use U-substitution. So the first example is this. For example, if we have the integral of x multiplied by sine x squared dx. Now the question is, how do we use U-substitution in this case? Now if we take a look at it, let's say we make our u to be x squared, and basically I just need to differentiate my du with respect to x, which is going to give me 2x dx. Now if I make x dx subject of formula, because I can basically write this as just the integral of sine of x squared multiplied by x dx, because a times b is still the same as b times a. So this is exactly what I just see there. Now here I can see x dx here, so that means if I make x dx the subject of formula, what am I going to have? I'm going to have x dx to be equals to du divided by 2. So if I substitute all these values here, what am I going to have? This means I'm going to have this to be the integral of sine. What is my x squared? That's u. Then what is my x dx? My x dx is du divided by 2. So this is how we use U-substitution. Basically just identify what is your u and what is your du, and just differentiate it. So how do we use substitution? So the primary thing is just to identify what your u is and differentiate it, then substitute it back inside it, the integral. So this is just going to give us, let's finish this up. This is going to give us 1 divided by 2, the integral of sine of u du. And if we integrate this, we're going to have this to be 1 over 2. If we integrate sine u, we're going to have negative cos u plus c, and which is negative 1 over 2, then the cos of u. So what's our u? Our u is x squared, then plus c, and we're done. However, if we ask some more complicated examples, how do we know when to use this substitution, or how do I know that I'm going to use this substitution? And that is exactly what I want to do in this video. For example, let's look at some cases. If we have the integral of f prime of x, then multiply by f of x to the power of n dx. This is exactly similar to this, like this is exactly something similar to this, but it's not quite obvious. But what this is telling us is that, for example, if I have a function raised to the power of n, whereby my n is not -1, and is being multiplied by the derivative of that function, so the answer of this is just exactly 1 divided by n plus 1, then multiply by f of x raised to the power of n plus 1. Let's take an example with regards to this result. Now let's take, for example, we want to integrate 3x multiplied by the square root of 1 minus 2x squared dx. Okay, so let's take a look at it again. Very well. We can see here that if we differentiate this expression here, I'm going to have something close to this, right? Don't take my word for it. Let's check it out. So let's take, for example, we say let our u be equals to 1 minus 2x squared. All right, so let's take the derivative of u with respect to x. So that means I'm going to have this to be, if I differentiate 1, I'm going to have 0 because 1 is a constant. And if I differentiate negative 2x raised to power 2, I'm going to have negative 4x, exactly negative 4x, then multiply by dx. All right, so now this can be written as the integral of 3 multiplied by 1 minus 2x squared x dx. Okay, so it's still the same thing. I just rewrote it. Right, so now if I make x dx subject to formula here, x dx subject to formula, I'm going to have this to be negative du divided by 4. And if I substitute it here, everything here, what am I going to have? I'm going to have this to be the integral of 3 square root of u, because this is u. Then what is my x dx? My x dx is this expression here. So if I put that there, I'm going to have this to be negative 4, negative du divided by 4. And I can substitute, I can just factorize it out because it's a constant. So I'm going to have negative 3 divided by 4, the integral of square root of u and du. And if I want to do this, I'm going to have the integral of u raised to power 1 over 2 du, and which is exactly negative 3 divided by 4, integral of, how do we integrate u raised to power 1 over 2? This is 1 over 2 plus 1 divided by 1 over 2 plus 1 plus c. Then we're going to have this to be negative 3 divided by 4, u raised to power 3 divided by 2 divided by 3 divided by 2 plus c. And we can write this as negative 3 divided by 4 multiplied by 2 divided by 3, then u raised to the power of 3 over 2 plus c. And we can finish this as negative 1 over 2. So what's u? U is exactly 1 minus 2 x raised to power 2, then raised to power 3 over 2 plus c. So one thing about using U substitution is the fact that when you've integrated it, you have to substitute back your U, the value of your U. Alright, so since we've discussed that, now how does this example relate to this example here? How does this problem here relate to this problem here? Okay, so if you take a look at it again, we can see that the integral here, let's choose it, okay, the integral 3x square root of 1 minus 2x squared dx is exactly the same thing as, we can still write this as the integral of 3x, not yet, this is 3x 1 minus 2x squared raised to power 1 over 2 dx. And we can see that our n here is negative, our n here is 1 over 2, which is not negative 1, so it passes test. And the another thing is that it's not yet in the best form. Okay, so because here we can rewrite this as, if we differentiate 1 over 1 minus 2x raised to power 2, we're going to have, basically we're going to have negative 4x. So if we differentiate 1 minus 2x squared, we're going to have negative 4x. Okay, so that means that we are having negative, here we're having negative 4x. So for us to have negative 4x, that means I can write this as 4. So I can bring out 3, then divide it by negative 4, then introduce negative 4 inside. So that means I haven't done anything. What I can cancel out this, take out this, and still have my original expression, which is this. Now the purpose of doing this is for me to be able to see that if I differentiate this, I'm going to have this. Okay, again, if I differentiate this, I'm going to have this. So once I have achieved this result here, and I can just use my quick formula. So I call this quick formula. So what does it state? It states that if you have the derivative of a function multiplied by the function raised to the power of n, it's just going to give you 1 over n plus 1, then multiplied by f of x raised to power n plus 1. And which is this going to give us? Just negative 3 over 4. Then here you multiply this by, you add 1 to the power. Okay, that's going to be 1 minus 2x squared raised to the power of 3 divided by 2, because 1 plus 1 over 2 is 3 over 2. Then multiply it by 1 divided by n plus 1, which is exactly 3 divided by 2. 3 divided by 2. Okay, then plus c. And this exactly is going to give us negative 3 divided by 4 multiplied by 2 divided by 3, then multiplied by 1 minus 2x squared raised to power 3 over 2 plus c, which will give us, you guessed it, it's going to give us this. Okay, so that's how we use the substitution. Another case whereby we use the substitution is when we have, let's take for example, we have the integral of 1 divided by x multiplied by ln x dx. Okay, so before I talk about this, before I do this integral, I would like to talk about something we all know about. You can recall that the integral of 1 over x dx is exactly ln of x plus c. Now, how do we know, or when do we use the substitution? We use the substitution exactly when we have derivative of a function divided by a function dx. This is going to give us ln of f of x plus c. And this is a good example for this problem. Okay, why do I choose this as a good example? First thing, let's try to use the substitution, the traditional U substitution. And how do I even know what should be my u? Okay, So basically, we can write this as 1 divided by x divided by ln x dx. Okay, so if I let my u be ln x, so what you want to watch out for in using u substitution is that you need to differentiate one of the expression there. For example, if I have 1 over x, if I should differentiate 1 over x, will it give me any of this expression here? That's the question we need to ask. This is basically negative 1 over x squared, so this is a no answer. However, if I should differentiate ln x, what am I going to have? I'm going to have 1 over x, right? So 1 over x is appearing in one of these expression over here, and that is actually a green light. But however, if I don't even know which one to use, or how do I know which one to use? Okay, so these are some times in which you use substitution. For example, if you have the derivative of a function divided by the function, so you know you want to use the substitution. And all you need to just do is to write it in all these forms. Like, for example, you can write it as f prime of x divided by f of x, or you can write it as this expression over here. You can write it as this expression, something like this expression over here, whereby you have the power, you can write it as a product of the derivative and the function raised to the power whereby the power is not negative 1. So these are some examples. So let's continue with our problem. So we have u to be equal to ln x. If you differentiate u, we're going to have 1 over x dx. And exactly that is what is appearing up here, 1 over x dx. So if we substitute it, that means we're going to have this to be integral of 1 over x divided by ln x dx is exactly 1 over u du. Okay, because u is ln x and 1 over x dx is du. So we have this. And this is exactly ln, you'll guess it, ln u. So plus c, and which is exactly going to be ln of ln x plus c, because our u was ln x. You all guessed it. Correct. However, if I want to use this formula over here, if I just want to use this formula over here, I can just say this is, once I write it in this form whereby I have the derivative of a function divided by the function, this is just going to give me the ln of the denominator, which is ln of ln x. Another quick example that comes to my mind is, for example, if we want to integrate tan x dx, right? So we can write this as the integral of sine x divided by cos x, all right, dx. So what do you observe here? If I should differentiate cos, I'm going to have negative sign, but here I'm having positive sign here. So what I can do is to insert a negative outside, then bring in the negative inside, because I know that negative will cancel out negative divided by cos x dx. And of course, if I should differentiate cos x, I'm going to have negative sine x. That means that's a green light. I can use this expression over here. So what's the answer? The answer is just basically going to give us negative of ln of cos x. Then we can add our arbitrary constant c. Good. So the last thing I want to talk about is the case whereby we have the integral of the derivative of a function multiplied by e raised to the power f of x dx. This is exactly just going to give us f of x plus c. Okay, an example is this. If we want to integrate x squared e raised to the power negative x raised to the power 3 dx. Okay, so what thing we notice here is that if we should take the derivative of one of them, if we should take the derivative of x squared, what are we going to have? And if we should take the derivative of e raised to the power negative x cubed, what are we going to have? And if we should take the derivative of, this should be the dx. it should be d dx. And if we should take the derivative of negative x raised to power 3, what are we going to have? Those are the three questions. Here we would have 2x. This one we would have negative 3 x squared a raised to power negative x cube, and here we're going to have negative 3x squared. Okay, so which one is closer to the U substitution here? We obviously can't use this because, I mean, if we differentiate this expression here is not close to this expression here, so we can't use this. And if we should differentiate this, we are having negative 3x squared. This is closer, but then we lost this expression here, which is still going to be appearing here. So this is out of the game. However, how about this expression here? If we are to use this expression here, if we should differentiate this, we are going to have negative 3x squared. However, negative 3x squared is not totally appearing here, but then we can force it to appear. And how can we force it to appear? Is by just writing it this way. We can introduce negative 1 over 3 outside, then we can introduce negative 3 inside. Then we have negative 3x squared. Then we have e raised to power negative x cube dx. Alright, so that means we have negative 1 over 3. So let's try to use we're trying to use our quick formula here. So basically we have negative 1 over 3. So if we look at this formula here, it says that if you have the derivative of a function multiplied by exponential of that function, that means the answer is just exponential of this function. So without loss of generality, the answer to this integral is simply negative 1 over 3. This is the derivative of a function multiplied by e raised to power the function. The answer is just e raised to power the function plus c, and we're done. If you don't believe me, let's try to use U-substitution for this problem. So let's write the problem again. So we have the integral of f prime of x, sorry, this should be x squared raised to power negative x cube dx. So here we let u be negative 3x squared, sorry, this should be negative x cube. And du is going to give us negative 3x squared dx because we are differentiating u with respect to x. So technically this was here. Then we just multiply both sides by dx. That means we have du to be negative 3x squared dx. And we just substituted everything here. What we have, just substituted it. Before we substitute it, we can write this as e raised to power negative x cube x squared dx. So to make this substitution make sense, we just want to make sure that we want to make x squared dx the subject of formula. So that means we're going to have this to be negative du divided by 3. Makes sense, because if I should just multiply this back, then that means I'm going to have my expression here. So that means this expression over here, that is the integral of e raised to power negative x cube x squared dx, can be written as the integral of e raised to power negative, sorry, so if this was our u is negative x cube, so this is u, then x squared dx is negative du divided by 3, which is negative 1 over 3 integral of e raised to power u du. And this is very famous. The integral of this is just e raised to power u plus c. And what was our u? Our u is negative x cube. So we have e raised to power, sorry, this was 3, then e raised to power negative x cube plus c, and which corresponds to our previous answer. So this is our previous answer, and this is our previous answer. So to bring everything to a cap, the point I'm trying to make is that here are some places whereby we can use the substitution. For example, if we have derivative of a function multiplied by the exponential of that function. So our mind should point out to U-substitution. Another point is when we have derivative of a function divided by that function. We can use U-substitution in this case. And the other point is if we have the derivative of a function multiplied by f of x, the function raised to the power n, whereby your n is not -1, then we can use substitution. And the overall general form is if we have a function of a function being multiplied by the derivative of one of the functions, then you have this expression over here. All right, so let's talk about a kind of integral whereby you can use U-substitution. The example whereby you can use U-substitution is, for example, if we have the integral of x, then e raised to the power -x to the power of 4 dx. Here, we can use U-substitution because if you take the derivative of this guy here over here, let's take derivative. Let's say u is -x raised to the power 4. If you take the derivative, you're going to have -4x raised to the power 3 dx. So here we have x, and here we are having x raised to the power 3. So we can use U-substitution, even if I should write this as e raised to the power -x raised to the power 4x dx. We can use U-substitution here. So we can only use U-substitution if these conditions have been satisfied. This condition I highlighted here have been satisfied. So this condition here, and this condition over here. So this is when we can use U-substitution, at least for basic integrals. Thank you so much for your time. I hope you enjoyed this video. If you enjoyed this video, make sure you give it a thumbs up and write your comment below. And also don't forget to subscribe. All right, thank you.